Pluto is a far-off and dumbfounding planet that was once essential to our nearby planetary systems family. However, upsetting declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a startling discovery. They propose that this icy world is on a potentially brief collision course with Neptune. But how could this occur, and what might be the consequences of such a colossal event? Are we seeing a looming impact? Or is there something else about this approaching massive mishap? Join us as we explore the potential results of a Pluto-Neptune collision. Pluto, a former planet that was renamed a dwarf planet due to its unusual orbit, remains a subject of interest and study in the vast astronomical community. According to recent forecasts by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially dangerous impact between these two planets, which could pose a significant threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its exceptionally bent shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, determined to be 17 degrees to the ecliptic plane. The way Pluto follows its path is much steeper compared to other planets. This inclination and irregularity add layers of complexity to its orbital design. Perhaps one of the most enthralling aspects of Pluto's orbit is its interaction with Neptune's orbit. For nearly 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, challenging our expectations of their positions in the solar system. This prompts the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to understand its strange orbit. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and irregular shape. The mystery deepened with the realization that Pluto's orbit indeed crosses Neptune's. The complexity of Pluto's orbit amidst these intricacies is evidence of the complexities of space mechanics. The three-body problem in space is about understanding how three objects, like Pluto, Neptune, and the Sun, move and influence one another with their gravity. It's like predicting where they will go based on where they start and how they pull on each other. In Pluto's situation, this problem illustrates how its orbit, Neptune's path, and the Sun's gravity all work together in a complex manner. Terms like alpha libration and degree libration, along with the VZK effect, are crucial to this puzzle. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. In the case of Pluto and Neptune, this term essentially means that when Pluto crosses Neptune's orbit, it is positioned around 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from affecting each other. Expansion libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it's situated well above their orbital plane, providing an extra layer of protection from potential impacts. Another significant factor in this scenario is the VZK effect, named after three researchers, Vaisala, Zippi, and Kozai, who studied how objects move in space. It explains how three celestial objects like Pluto, Neptune, and the Sun pull on one another with their gravity. In Pluto's case, the VZK effect helps us understand why its orbit around the Sun is so unusual. Despite Pluto's orbit seeming erratic, this effect helps keep it moving smoothly. The VZK effect demonstrates that although space may appear chaotic, certain patterns and rules maintain order. These factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or veer off course. This three-body problem is essential for understanding how these orbits change based on the gravitational pulls of celestial objects. Mathematical simulations in the late 1980s revealed that despite these stabilizing factors, Pluto's orbit is still relatively chaotic, with minor variations in initial conditions leading to significant differences over millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over exceptionally long periods, effectively keeping chaos at bay. Recent computer models have helped us comprehend how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has an intriguing relationship with Pluto, where for every 3 orbits Neptune makes around the Sun, Pluto completes 2. This connection helps keep Pluto's orbit stable. Neptune isn't the only contributor. Jupiter's gravity also plays a major role in safeguarding Pluto's orbit, with Saturn contributing significantly as well. Simulations show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a stable orbit for a long time, even billions of years. It appears that Neptune, Jupiter, and Saturn work together to ensure Pluto continues to move safely through space. These phenomena are critical to the solar system's stability. Without these forces, the solar system as we know it would be a place of much greater disorder, and celestial bodies like Pluto could crash into others or be ejected from their stable orbits, causing a domino effect. Understanding Pluto's orbit is crucial for comprehending the dynamics of our solar system. The case of Pluto shows how even the most seemingly unstable orbits can achieve a state of stability through gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and investigation of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the peculiar nature of celestial bodies, and Pluto's orbit is a prime example of this phenomenon. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is vividly illustrated by Pluto. This means that even slight changes in Pluto's position or speed can significantly alter its long-term trajectory. In the vastness of our solar system, Pluto occupies a unique position that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant discoveries about its structure and behavior. One of the most captivating aspects of Pluto is its surface, an intricate tapestry of ice, rock, and various compounds. The New Horizons mission, which flew by Pluto in July 2015, provided remarkable data about this distant world. The surface of Pluto is characterized by vast plains, towering mountains, and deep valleys. One of the most remarkable features is Sputnik Planitia, a massive, heart-shaped plain primarily composed of nitrogen ice. This region showcases a diverse array of landforms, including massive ice shelves and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active despite its vast distance from the Sun and extremely low temperatures. Another intriguing aspect of Pluto is its atmosphere, which is primarily composed of nitrogen with traces of methane and carbon monoxide. Pluto's atmosphere is tenuous yet displays fascinating seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior reflects the complex interaction between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. Pluto's interaction with its largest moon, Charon, adds further complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that both bodies are in a mutual orbit around a point in space that lies between them, rather than Pluto simply orbiting Charon. This unique relationship contributes to the complex gravitational dynamics in the region, influencing the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to various other dwarf planets and potential impactors. This belt serves as a reservoir of ancient material from the early solar system, offering scientists a glimpse into its formation. Pluto's orbital characteristics may provide insights into the evolutionary patterns of these distant objects, suggesting that interactions with larger planets have played a significant role in shaping their current orbits. Understanding Pluto's orbital dynamics has broader implications for our understanding of the solar system's evolution. Gravitational interactions from neighboring giant planets, such as Jupiter and Neptune, can alter the trajectories of smaller bodies, including those in the Kuiper belt. These interactions can lead to orbital changes, possibly resulting in collisions or ejections from the solar system. As scientists continue to explore these interactions, they may uncover broader patterns governing the behavior of celestial bodies throughout the universe. The study of Pluto also raises philosophical questions about classification in astronomy. The decision to reclassify Pluto as a dwarf planet in 2006 was controversial, sparking debates about what constitutes a planet. Pluto's orbital relationship with Neptune and its position in the solar system serve as powerful reminders of the complexity of the universe. Through continued exploration, we can expand our understanding of these distant worlds and the forces that govern their motion. Continuing our exploration of Pluto's fascinating orbital dynamics, it's essential to recognize how the gravitational forces exerted by distant planets shape the behavior of objects in the outer solar system. While Pluto's orbit may initially seem chaotic, it is precisely these intricate interactions that allow it to maintain stability despite the apparent disorder. By delving deeper into the mechanics of Pluto's orbit, we uncover more layers of complexity, shedding light on the dynamic processes that govern the motion of celestial bodies. One intriguing aspect of Pluto's relationship with Neptune is the long-term stability of their orbits, despite their occasional proximity. This is due to a unique resonance between the two bodies, known as a 3:2 orbital resonance. For every 3 orbits Neptune completes around the Sun, Pluto completes 2. This resonance keeps Pluto and Neptune in a stable configuration, preventing them from colliding despite their orbits crossing. The stability provided by this resonance is an elegant example of how gravitational interactions ensure the orderly movement of celestial objects. This 3:2 resonance is a result of the gravitational tug-of-war between Pluto and Neptune. Each time Pluto and Neptune approach each other in their orbits, their gravitational fields interact in a way that ensures their paths remain synchronized over long periods. The result is a system where, even as Pluto crosses into Neptune's orbit, the two bodies are always carefully separated by the steady resonance, making the likelihood of a collision practically non-existent. The 3:2 resonance between Pluto and Neptune is not just a random occurrence, but a finely tuned gravitational relationship that highlights the intricacies of celestial mechanics. This resonance stabilizes their orbits, ensuring that despite their apparent orbital overlap, they never come into direct contact. This phenomenon exemplifies how gravity can create harmony within apparent chaos, maintaining the structural integrity of the outer solar system. Interesting.